Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Professor of Astronomy here at Foothill College in Los Altos Hills, and it's a great pleasure for me to welcome everyone here in the Smithwick Theater and everyone watching us on YouTube or listening to our podcast to this lecture in the 24th Annual Silicon Valley Astronomy Lecture Series. These programs are co-sponsored by the Foothill College Science, Technology, Engineering, and Math Division, by the SETI, Search for Extraterrestrial Intelligence Institute, and by the Venerable Astronomical Society of the Pacific, and we're very grateful to them for their help in getting the word out and helping us with speakers. Also tonight we had help from the Kavli Institute at Stanford University in publicity because our speaker is from Stanford. The lecture series is available on YouTube and on all the different channels where podcasts are available. And if you're listening or viewing this for the first time, we hope you'll go back and look at our greatest hits over the last 24 years. All right, and with that, let me now introduce our speaker tonight, Dr. Brian Lantz of Stanford University. It's really exciting to have him here because in a way, we are at the beginning of a whole new dimension of astronomy. We're calling it multi-messenger astronomy, where we're seeing the universe not just the ways we've been seeing it for decades and centuries, but in a whole new way, pioneered by the group that Dr. Lantz is part of. This is gravitational-wave astronomy, and it's very similar to when silent movies switched over to sound, and there was a whole new dimension to appreciating movies. In the same way, our exploration of the universe has switched over to a multi-dimensional way of appreciating and exploring the universe. Our speaker, Dr. Brian Lantz, is a senior research scientist at Stanford University. He started working on the Laser Interferometer Gravitational-wave Observatory, or LIGO, in 1991 as an undergraduate in the laboratory at MIT of Nobel laureate Ray Weiss, and continued there at MIT to get his PhD, building high-power interferometers, which were the prototypes for what eventually went into LIGO. Dr. Lantz is now the scientific leader for the Advanced LIGO seismic isolation system, and you'll learn more about that in a minute. And he is designing new mirror suspensions to upgrade Advanced LIGO. And he wants you to know that he loves tinkering with these amazing machines. So it's my pleasure now to introduce Dr. Brian Lantz.
Thank you very much. It's a pleasure to be here. Good to see so many folks brave the rain to come out. I want to talk to you about a new, well, relatively new kind of way to do astronomy. Actually, the multi-messenger astronomy came up in the introduction there. You can actually see, this is sort of my favorite picture of multi-messenger astronomy. This is an artist's rendition of two neutron stars crashing into each other, making a huge explosion with a lot of light coming off, a jet of gamma rays, and you can see the little ripples in the background there of the gravitational waves coming off. I hope this is a fun talk. It should be. We've got lasers and black holes and Einstein and giant machines and tiny little measurements and huge explosions, all kind of tied together by gravitational waves. I should definitely say that this is a huge project, right? There are universities from around the world. Thousands of people have been working together to make this happen. Of course, Stanford right here is my favorite, but it's definitely a big collaboration. We're funded by the National Science Foundation and a bunch of other international partners, which is absolutely critical for making this thing go. Before I kind of get into the whole gravitational waves, I want to remind you about sort of two terms that I'm going to be using a lot, so I want to make sure everyone's kind of on board. Black holes and LIGO. So black hole, this is a small, massive thing in outer space. The gravitational pull of a black hole is so strong that not even light can get out. Now, you can compare that to like my favorite star right here, the sun, and here's a sort of a NASA picture of that. It's about 865,000 miles across. The mass of the sun, if you're an astronomer, mass. Okay. We hear solar masses a lot. My audio is kind of cutting in and out. Hopefully it'll keep going. If you were to take the sun and squash it down from 865,000 miles to something that's tiny, right? The surface gravity of that would just keep getting stronger and stronger as you smushed it down. And when it got to be about 3.5 miles across, with one solar mass on the inside, the surface gravity of this is so strong that even light can't get out. Astronomers, they call this a compact object, which is a massive understatement, okay? There's a couple more of those coming up. A compact object. Our sun is not going to do this. On the other hand, what LIGO looks at are typically something about 30 solar mass black holes. So these are about 30 times the mass of the sun, jammed into an event horizon, which is where the light can't get out. The mass actually kind of goes all the way down to a point in the middle, which seems weird. But there's this kind of event horizon about 110 miles across where the gravity is so strong that light can't get out, which is why it's called a black hole. Okay. The other term that we kind of need to know is LIGO, which is the Laser Interferometer Gravitational Wave Observatory. Here's a picture of the two LIGO sites right here. I'm going to tell you about laser interferometers. I'm going to tell you about gravitational waves. And I'm going to tell you about the cool observations we're doing. So like the name LIGO is actually like a kind of an outline for my talk. All right. We are part of a international network. So LIGO's got two sites, Washington State and Louisiana. The Europeans run a detector called Virgo in Italy. There's a German-Scottish, German-UK collaboration called Geo600 running a short interferometer in Germany. The Japanese have the very high-tech cryogenic gravitational wave detector in a mine, although it's not running right now. There's a big earthquake. And LIGO India has approved construction for a third LIGO detector in central India. Having a network like this is absolutely critical if you want to have reliable detections, have machines up 24/7, and be able to figure out where the events were. Of course, we sort of turned in from a crazy physics project to actually doing astronomy on September 14th, 2015, when at the LIGO Hanford and the LIGO Livingston observatories, we saw these signals. So these are the first gravitational wave signals that we've ever seen. This is the data from LIGO Hanford. You can see this is kind of instrument noise, and then you start to see the signal here, and it's getting faster and faster and bigger, and then it stops. Here it is at LIGO Livingston. You see the same waveform at two observatories that are 3,000 kilometers apart. Gives you some confidence that it's actually coming from outer space. Here they are lined up. You can see like this is nice, clean signal. This is instrument noise. The astonishing thing to me about... Could you try again? I'm trying. The astonishing thing to me is if you look at the amplitude of this signal, we measure it in strain, which is a proportional stretching of space-time. The strain is 10 to the minus 21. It is a very, very tiny strain. The amount of space-time stretching we're getting is very, very close to zero. But you can clearly see this signal, right? These machines are amazing. All right, so that's LIGO. What is a gravitational wave, right? So here's a famous gravitational guy, Isaac Newton. He described gravity as a force. I only have two equations in this whole talk. This is one of them, right? So even my 13-year-old and his friends out here have probably seen this. The force of gravity is constant times the mass of the two objects divided by the distance between them squared. This is an amazing theory because it describes both like what happens when you drop something, right, and the orbit of the planets. And yet, like even Newton realized that there were some really big problems with this theory, right? I mean, this apple's got a big gravitational field, right? If I were to suddenly move the apple, accelerate it to some new place, right? If you believe this theory, right, that equation right there, just as it's written, what that tells you is that the force from gravity of this apple instantaneously changes across the entire universe, right? Which is clearly wrong, right? We don't think that the information can travel at faster than the speed of light. Newton actually pointed out that this was wrong, but he didn't know what the right answer was. So in 1916, Albert Einstein came along and said, actually, the universe is much more strange than that, right? It's not like you have a big empty stage and you have a few actors with their gravitational fields on it. Actually, the whole space is participating, right? There is this space-time metric where all of our objects sit inside of, and the mass of the object distorts the space-time metric. And the curvature of that metric tells the objects how to move around, right? Maybe you've seen like in a NOVA show, like space represented by this great big rubber sheet. You got the sun and the earth on here bending this sheet, right? Distorting it. And as the objects move around in that gravity, the bending of this sheet is what tells them how to move around. And when you start accelerating the objects, right, the bending of that sheet, those ripples in that travel out at the speed of light. And I am not going to tell you any more general relativity, but I will show you a fun little movie. And maybe you can kind of visualize sort of what's happening here. So this is a movie that was made after the first detection. These are the two black holes from the first merger. They're spinning around. Here you can see this sort of representation of the metric of space-time. Here you can kind of see the gravitational waves propagating along at the bottom. These two black holes are spinning around. They're emitting gravitational radiation. The energy is getting carried away. The orbits are getting closer and closer. But watch what's happening to the metric right here, the space-time. These guys are spinning in. We're about to slow down to about 100 milliseconds from merger here. We're going to slow down there we go. We're going to slow down the movie. The space-time starts getting really stretched out and distorted. And if you watch how those little ripples travel out now through the space-time, that's kind of the representation of these gravitational waves that we're trying to measure, right? It's a really interesting way of watching the extreme distortion of the space-time right in the middle. All right, so how do we measure something like that? Okay, so put that down before I drop it. Here you got your two black holes that are whizzing around each other. You got some gravitational wave coming off to Dr. Smiley here, right? Ring of free particles hanging out in space. It's a transverse wave. As the wave comes through, let's say folks in the back were to suddenly explode in a supernova or two neutron stars crashing into each other, and a wave comes along like this, right? What you see is that the space would distort and stretch out in one direction and compress in the other. And then as the wave kind of comes past me, right, it'll oscillate back and forth in an ellipse like this as the wave kind of comes past, and then when the wave passes all the way back, things kind of go back to normal. And so if you had a way of measuring some objects that you put in space, like two mirrors out here in the middle, out here at the end, and a beam splitter in the middle, when the wave went past, you would see one arm get longer, the other arm get shorter, and then as the wave continues on past, they would change their direction, oscillate back and forth a couple of times, and finally come back. That's how LIGO works, right? There's a beam splitter here, these long arms, and we measure the distance with these with a big laser system. I'll show you a little bit more about that in the middle. This is kind of weird, though, because the mirrors, when the gravitational wave go by, the mirrors don't actually move, right? Those mirrors are perfectly happy sitting with no acceleration right where they are. Actually, it's the space between the mirrors which is stretching out. And if you think that's a perfectly normal, reasonable thing, raise your hand. No. It's weird, right? It's significantly weird. All right. And they're hard to measure, right? The gravitational waves are hard to measure because space-time does not like to be stretched, right? So the original strain that we measured is 10 to the minus 21. So the length change of these 4-kilometer arms was only about 4 × 10⁻18 meters. So an atom is about 10 to the minus 10 meters. A proton is about, what did I say, 1.7 10 to the minus 15 meters. The wobbling that we're looking for the length of these arms is something like 500 or 1,000 times smaller than the diameter of a proton. It's cool, right? It's a really, really tiny number. We're going to go from a really tiny number to a gigantic number in just a minute. Yeah, so that's why it's taken so long to see, right? I mean, Einstein predicted these in 1916. Ray Weiss wrote a paper in 1973 kind of showing how you might be able to build a machine to measure them. And it wasn't until 2015, almost 100 years after Einstein predicted them, that we finally measured the first one. All right, so 3 things to make a machine like this work. You got really long arms, you have really quiet mirrors, and you have a very precise measure of the distance between the mirrors. I work on the instrument, so most people don't talk about this in LIGO, but I just can't help myself. All right, so strain is the delta length over the absolute length. So this delta length is the strain times the length. So the more length you have, the more length change you get, right? And if you're trying to measure a really small length change, you want a really long arm. Our arms are 4 kilometers. Our arms are 2.5 miles long, which is a big, big machine. We're the world's, we used to be the biggest, and then we're the second biggest. Now we're the third biggest like ultra-high vacuum system. Here's a picture of that arm getting built. It's a big steel tube inside a concrete enclosure. Here it is after it's all finished up. We're in Louisiana. It's really quite pretty. It's actually a lovely site to go visit, although don't go in the ponds. Sometimes alligators climb in there. So you got long arms. You get really quiet mirrors. So if you take a look, if you sort of think about this little mirror right here in my schematic, this is what the LIGO vacuum system looks like. So this mirror is in its own vacuum chamber out at the end, connected to everybody else by these long pipes. And if you were to kind of do a cutaway of that, what you would see is a big seismic isolation system. That's what I work on, with a big mirror suspension hanging down. The motion of this mirror is about 10 to the minus 19 meters in a 1 hertz bandwidth at 10 hertz, which doesn't really mean anything to most of you. It's just a really tiny number. It's about 30 billion times less motion than you have of the ground. So there's a 7-stage isolation system trying to keep that mirror from moving. It's very successful. That mirror is one of those mirrors, there are 4 of them, right, at each site. Those are some of the quietest places on the planet. Although I don't know of any list that lists places like that. Anyway, here's a picture of the isolation system. It's got big springs, it's covered with sensors, it's got actuators. We use springs and masses to keep it still. We use feedback control and the sensors and actuators to keep it still. Kind of every trick you can think of we're using. Here's there we go, picture of the LIGO suspension. This thing's about a little over 6 feet long. It's a big piece of glass at the bottom. It's about a 90-pound piece of glass, 34 centimeters in diameter, 20 centimeters thick. It's hanging on a 4-stage suspension. It has the best optical coatings that money can buy. People at Stanford and other places are working on making them even better. It's a huge topic of research right now. And if we do it right, the motion of that optic at 10 hertz is set by the thermal drive. So just because it's warm, it's vibrating. And that dominates the motion of the optic. Now, why do we use a 4-stage suspension? I'm glad you asked. I actually brought a model of the LIGO suspension here to kind of demonstrate how this works. So here's a model of the LIGO optic. Very accurate, as you can see. It's hanging on a rubber band. And so if I move around my suspension point at low frequencies, of course, the optic just follows along. And if I move it at the resonant frequency, then the motion of the optic is much bigger than the motion of my hand here, which is why there are little sensors all around the LIGO optics. But if you move the suspension point fast, out at 10 hertz, which I can't quite do with my hand, what you see is that this mass spring isolates the optic. And so the optic moves a lot less than my hand does. You can do it horizontally too, maybe. Right? And of course, LIGO uses a 4-stage suspension because if 1 is good, right, 2 is even better. right? Let's see if I can get this whole thing still here, right? So now you can see I can move my hand really rather a lot. And the optic is very well isolated. So this is basically the trick that LIGO, Virgo, Kagra, Geo, all people use this to keep their optics very quiet. All right, so here's the engineering prototype for the Advanced LIGO optic with Betsy Weaver, who's the lead installer for these and now the lead operations person up at LIGO Hanford. She's good for this picture because she's kind of short, so it makes the suspension look even bigger. And here it is with the real optics installed. They're really quite pretty. The other thing you do is you try and measure the distance between these optics very carefully. So you do a bunch of optical tricks. This is basically a Michelson interferometer with some extra juice added to it. I've added some more mirrors in here, which we use. I'll talk about a few of them. The basic idea is just a Michelson interferometer. This is what Michelson and Morley used back before people understood, like when they were looking for the luminiferous ether that Einstein finally explained to everyone that it didn't exist, right? So you got there we go. You got a laser, light comes out, hits the beam splitter, splits into these two arms, and as the arm lengths change differentially, you get light on your photodetector. So what's happening here is you can think about the electric field in these two beams. The beam goes out, its electric field is there, comes back, the yellow one in the X arm, the blue one in the Y arm, they recombine and we set it so that these two fields are out of phase, so when you add them together, they add to 0. There's no electric field, there's no light, and there's no light on your photodetector. But as you change the mirrors a little bit, the phase of these two electric fields change. And the interference changes a little bit. And instead of being just 0, as these two waves kind of line up with each other, now you get light on your detector and you can see it. So what you've done is you've built a ruler. It's 4 kilometers long. And the ticks on that ruler are the size of a wavelength of light. They're only, for us, it's a 1 micron laser. This is interferometers are an amazing way of measuring things. We do some more tricks. We bounce the light back and forth about 300 times between these mirrors. This is sort of like having your arm that's 300 times longer, sort of. We're limited by our ability to count photons. So we have a 60-watt laser in here. We store the light in the arms, but we also store it in what we call the power recycling cavity. By the time we're done, we have 3 kilowatts on our beam splitter and almost 400 kilowatts of light bouncing back and forth in each arm. And this is a frickin' nightmare, right? Having 400 kilowatts of light, 375 kilowatts of light on your mirror is just terrible, right? Anyway, but it's really good for measuring gravitational waves. So, there you go. The plan pretty soon is to move it up all the way up to 750 kilowatts. We'll see if we can get there. So now, right, now you run this machine and you just listen, right? You got long arms, you got quiet optics, you're measuring the distance between the optics very carefully, and you just wait for something to change the distance between them, right? Something unusual, right? Like the first gravitational wave. So here it is again at the 2 sites, Hanford and Louisiana. This is the actual signal. This is the best numerical relativity fit to a gravitational wave. And when you take this minus this, you get the instrument noise left. This is called a spectrogram. I've got one more of these, so let me tell you what this is. This is a plot of the frequency as a function of time. So here you can see it's kind of a low frequency. So here you can see the powers at a low frequency, kind of 40-ish hertz. And then as you move through the gravitational wave, it gets faster and faster, so the frequency is going up. Does that kind of make sense? Right? We call this a chirp, right? It kind of starts at low frequency, woo. And as the gravitational wave goes past, the frequency goes up, whoop, like that. Now you try and do a fit. You use your big computers and you can do a best numerical relativity fit to the signal that you see, and you try and figure out what caused that signal. So for us, we think it was a 29 and a 36 mass of the sun, solar mass black hole, whizzing around each other. You can see they're getting faster and faster. So they finally merge right here and end up as a single spinning black hole. That black hole is spinning really fast. This is a plot of the velocity of these two guys going around, right? So this is 0.3 of the speed of light. So you got two objects 30 times the mass of the sun, and they're whizzing around each other at a third of the speed of light. Now, I said that you need an acceleration to make a gravitational wave, right? I mean, I'm making gravitational waves right now, right? But you can't see them. You need a lot of mass and a lot of acceleration. This is a lot of mass and a lot of acceleration. You know, by the time they merge, they're moving at over half of the speed of light. And it forms a single black hole at 62 solar masses. And I'm wondering if any of the folks in the audience are trying to do math here. Because 29 plus 36 does not equal 62, right? It equals 65. 3 solar masses have been converted into gravitational radiation. Like Einstein tells us this, E equals mc squared, right? E equals mc squared, right? 3 solar masses have been converted into energy. This whole signal is only, what, 0.2 seconds long? This is an enormous power, right? It's just so freaking big, right? In fact, if you think about how many watts are coming out of this, and you compare it to all of the light coming off of all of the stars in the visible universe, this is 50 times bigger, right? This is a huge, huge explosion, right? For a split second, this is by far the brightest thing in the universe. And we would have totally missed it. You'd never see it, right? You don't see it, right? You look in the sky, you don't see these things, right? Nothing to see, right? It's just space-time wiggling around, right? If we didn't happen to be running the observatories, like on the night before the observation run was supposed to start, kind of warming them up, this would have gone right past us and no one would have ever known. And if you want to think about how weird is the universe, right, that the brightest event would have happened, no one would even know, right? It's really weird, right? What else is out there? I have no idea. Okay. So the black holes merge kind of around 100 hertz. So if you actually take that signal and you play it on your headphones, you can hear it. What I want to do right now, I want to play you the sound of those black holes merging. So the first thing is the noise of the detector, right? I'm going to go back. All right. I went too fast. There's a roar at the beginning, right? That's the noise when there's no signal. Then you hear the little boop. That's the gravitational wave, right? That's the unusual thing that we're looking for. Then it's going to play that twice, and then it's going to frequency shift it up by 400 hertz to kind of put it where you can hear it a little better, and you'll really be able to hear the chirp. So let's see if we can hear that black hole, those black holes merging. Let's go. There we go. Hear that chirp? It sounds kind of corny, but actually when you're in the control room working on the interferometer, listening to the machine with your ears is actually a very effective way to do debugging of the noise, because your ears are really good at kind of picking stuff like that out. Anyway, so that's cool, but if you're looking for gravitational waves and you don't care about the rest of astronomy, you're like, that's fine, but all the rest of the astronomers are like, hey, I want some signals too. How about some multi-messenger astronomy? So the other kind of famous signal that we have is the merger of 2 neutron stars. Now, these are compact objects. These are burned out stars, about 1.4 times the mass of the sun, and they're made of kind of the same stuff that the nucleus of an atom is. So they're very strange, but they're actually stuff, right? Here's sort of an artist's rendition of one hanging out over San Francisco. Presumably it's looking for a apartment, having a hard time. On August 17th of 2017, we actually measured the first one of these. We saw it come in at Hanford. Livingston, there was a big glitch. We didn't actually see it at Livingston first. But we noticed that the Fermi satellite, the Fermi gamma ray burst monitor, the Fermi satellite actually saw a burst of gamma rays about 1.7 seconds afterwards. So somebody went back and looked, realized there's a big glitch right here, pulled it out, and now this looks like a really pretty spectrogram, right? Like I was showing you before, except look, it's like 30 seconds long. So these are lightweight objects, so they just take longer to merge, right? And you see this beautiful spectrogram. You see it at Hanford, you see it at Livingston. Weirdly, you don't see it at Virgo. You should have seen it at Virgo. Virgo was running, the noise was pretty good. It turns out that it was coming from a direction. Mostly these observatories can see in all directions, but there are 4 directions where they can't. If the signal comes in right between the arms, you can't see it. It's like, oh, well, now we can use when the signal arrived, or didn't, at the 3 sites, and you can triangulate where it came from, right? So you can make a map on the sky, and you're like, it's right in here. Actually, gravitational waves also help you find the distance to an object. Skip that for now. There are 53 galaxies in here. And so as soon as the sun went down on the southern hemisphere, the big telescopes in Chile all started looking for it, right? And 10 hours after the merger, they got this nice, bright little spot that shows up. Here's that same galaxy 20 days before, no spot, bright spot. They put this out on the network, and before you know it, there's this huge collection of astronomers. Basically, everybody in the southern hemisphere who's got a telescope turns and looks at this thing, right? It is an amazing collection of data. I actually brought, so this is from a paper down here, sort of describing the history, like the sequence of observations, right? In gravitational waves, gamma rays, X-rays, ultraviolet, optical. See all these optical telescopes, right? The infrared, the radio, right? So this is, actually, this is not the paper. This is the list of authors, right? Right? I'm in here. Hold on. There I am. See? There I am. And their affiliations and the funding sources. This is 37 pages of small print, right? It's a big deal. People are super excited. And when you look, you can see like here's the gravitational waves. 1.7 seconds later, you get the gamma rays. You see it in a bunch of different optical instruments. Here you can watch it in the infrared. This is visible, but these are spectrograms looking at the cooling. This is sort of a spectrum at 1.2 days, 1.4 days, 2.4. You can see this peak is moving over as the thing cools off. Here it is in X-rays. It didn't show up for 9 days. We don't know why that's true. There's some theories, a bunch of theories, right? Here it is in the radio. It's coming on in about 16 days. It's a huge, cool piece of astronomy. Anybody have any gold jewelry on? Yeah. The gold that we have on this Earth probably mostly comes from the kilonovas, the 2 neutron stars like this, crashing into each other sometime before our solar system formed. So there's some real impact for this kind of astronomy on, on your romance and your love life, right? Mine too. So where are we now? Right? Those are my 2 favorite events that we've seen so far. What LIGO does is it takes turns between observing and upgrading the instrument. So observing run 1, 02, 03. We've published all the data by 03. We're right now in the middle of 04, which started back in May of this year. There's a little break to kind of do some upgrades. It's going to run through the end of 2025. So the end of 2024, sorry. Then we're going to upgrade we're going to start the next set of upgrades. And so what have we seen, right? Those are the 2 famous events. This is the cumulative event rate. So you can see over the last little over 1,000 days, like the event rate really picked up in 03. There were 90 events by the end of the 3rd observing run. And then during 04, we've gotten 81 more significant, what do they call them? Candidate events, yeah. You can actually go and watch those candidate events come in. You can go to gracedb.ligo.org and you can like watch the signals arrive and see what we're learning about them. The full paper on this is going to be a little while. This is sort of an artist's version of all of the signals through the end of the third observing run. And what you see here, sort of arranged by what makes it look cool, all of the blue things on here are black hole mergers. So you start with 2 and you end up with 1. The red signals are black holes that we've seen other ways. Yeah.
03 refers to the year 2003?
It's the third observing run. So it ended in 2020 when the pandemic started. Yeah. So third observing run here after we've been running for, I don't know, 720 days, something like that. These little yellow dots are neutron stars that other people have measured, and the orange ones are things that LIGO has measured. And so you can look at this plot and you're like, wow, like we've seen a much bigger range of black holes than anyone's ever seen before, and a lot more. Some of these things are like this weird kind of, is it orange or is it blue? Is it a neutron star or a black hole? There's this funny gap in here where we haven't really seen almost any events before now. LIGO and Virgo and Cogger have seen several in here. It's a little bit of a mystery what those are. Trying to get some more data. It's cool that there's actually something there. That's new. Let me tell you about one of these big fat ones. So GW 190521, so 2019, May 21st. There's an event which is about 150 solar masses total. Here you can see it at the 3 sites, nice, clean signal. It doesn't look like the previous one, though. You're like, that's cool. You know, it looks like this mass is about 85 times the mass of the sun. This one's about 66 times the mass of the sun. You're like, that's cool. It's a big black hole, right? That's neat. But, so I'm reading through the paper trying to get ready for this talk, and they're like, well, you know, this is interesting because this seems to be in the pair instability mass gap. And you're like, pair instability? What is a pair instability? Well, it turns out when you make a black hole, what you do is you take a big star, right? Burns hydrogen, burns helium, there's fusion, it kind of burns up to oxygen. The oxygen kind of sits in the middle, burns along, and just big bright star. If you get more than about 30 solar masses of oxygen in the middle of a big fat star, instead of just doing the normal fusion thing that you see like in our star, right, you start to generate, according to the nuclear physicists, antimatter, just a little bit. You start to generate anti-electrons, positrons, right? And so the pair here is a positron and an electron, matter and antimatter pair, and when those two things touch, right, they disintegrate into energy, right? And suddenly the middle of your star, if it's more than about 65 solar masses, instead of eventually cooling off and forming a black hole, you get a lot of antimatter production. It suddenly gets extremely hot and it just blows the whole thing up as a supernova. This is what astronomers call an instability. Yeah. So you shouldn't be able to make something that's 85 solar masses, and you're like, well, okay. How to get there, right? So immediately people start coming up with various theories. There's a whole bunch of theories that gets there. It's really exciting because now there's actually some data that all the theorists can start pushing the theories against and comparing. Now, it's hard to figure out which of the alternate theories is right because there's only like kind of 4 cycles in this whole thing, right? So to get better understanding, you really need to get more signals like this and better instruments, which is what I do, right? Okay. I'm going to skip this. Yeah. This is talking about the Hubble constant. I'm just going to keep going, though. There's a lot more to see, right? I told you some cool stuff that's going on about LIGO. This is a plot of the kind of signals that might make gravitational waves and where LIGO sits in its ability to see them. So these are signals at about 100 hertz, sort of a 10 millisecond orbit time. Here's stuff in about 2 minutes. These are massive binaries, 10 to the 6, 10 to the 7 solar masses, or like a black hole falling into the big black hole, a little black hole falling into the big black hole in the middle of our galaxy. I guess there's a talk about that next time. Or maybe giant black holes, like 1 billion times the mass of the sun, herking around in the middle of other galaxies. Maybe something left over from the Big Bang. A lot of stuff to see, and so of course, LIGO can see kind of this stuff, the stuff that's above our curve, right? But people are looking a bunch of other ways. Let me tell you about some of the stuff that's coming up, right? LIGO's got some big ideas for improving, getting a lot more signals here. LISA is a space-based version of a gravitational wave detector. And the Pulsar timing arrays have actually measured something. So let me tell you about a couple of those. So here's 2 pictures showing the European and the American versions of upgraded detectors, the Einstein telescope and Cosmic Explorer. It's sort of 10 kilometers long, underground. It's hard to get space in Europe. In the US, we're talking about a 40-kilometer, maybe a 20-kilometer long L-shaped machine. Other configurations are possible. And why would you do this, right? So if you look at sort of us looking out at the edge of the universe, right? Kind of past redshift of 100. So we're here in the middle. O3, that third observing run, can see out to about this distance when it's looking for black holes, right? And little white dots here are sort of a simulation of the expected number of black hole mergers that you might see. So we can see a little bit farther than that, and we're seeing a bunch of mergers. This is the distance to which you can see neutron star mergers. That's that first one I showed you, 170817 is what we like to call it. We've got one, a couple more maybe out here that are coming up, I don't know. When you go to these third generation machines, your distance to which you can see black holes is going to go like this, right? So here's Cosmic Explorer and Einstein telescope in the pink and the blue. And when you say, like, what does that get us, right? Here's kind of the population of black holes that you're going to be able to see. It's a lot. It's a lot. It might be all of them, right? All of the 30 solar mass black holes that collide in the universe, we might be able to see them all. That would be super exciting. And then you think about, like, what about the neutron stars, right? I think the neutron stars are even more impressive. Like, the rate at which you're going to see neutron star mergers should be astonishing. So if your congressman asks if you think that she should fund next generation gravitational wave detectors, you should say yes. All right. LISA. LISA is a thing like LIGO, but it's in outer space. And if you think 40 kilometers is long, you'll be amazed to hear that the arms of LISA are almost 2.5 million kilometers long. It's 3 satellites orbiting around the sun, kind of behind the Earth. The European Space Agency just gave this the official approval just like 2 weeks ago. It's super exciting. The launch date is set for 2035. 2 cool facts. You should be able to watch black holes that are 1,000 solar masses merging with each other. You should be able to watch things like our sun. When it burns down, it's going to be a white dwarf. There should be so many white dwarf binary systems in our galaxy that it's going to be hard to tell them all apart. Like the little weak ones that just kind of merge into each other. There's so many signals for LISA to see. And if you think that 2.5 million kilometers is a long way, I do, right? Let me tell you about the pulsar timing people, right? So what we're doing right now with these guys, I have nothing to do with nanograph, right? I just think this is cool. There are these stars called pulsars, and they make very regular ticks, tick, 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 and you can watch them with big radio telescopes. This is the VLA. If the distance between us and that pulsar were to suddenly stretch out, right, the pulsar up here, goes doot, 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 like those ticks would get farther apart for a little bit as the Doppler shifts away from us, right? And if it starts Doppler shifting back toward us, it goes tick, 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 tick. Tick, 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 like this. And you could watch the modulation of those pulses as the distance from us to that pulsar changes, right? Here's the Earth. Here we are looking at those pulsars. Nanograv, which is a US facility, been watching 68 of these pulsars for the last 15 years, right? So if you got two pulsars, there's a gravitational wave coming in from the back of the room, and they both start moving away from this, they'll be kind of moving together. That modulation will be moving together, right? As they get like that, right? But if you watch a pulsar over here, what you'll see is as this one moves away, this one will move in as a gravitational wave goes past, right? And so you should see this differential modulation of the pulses, and that's just what Nanograv announced on June of 2023, last summer, right? So here they're looking, this is a complicated plot, but here you can see for pulsars that are in the same direction, there's one kind of modulation on those signals, and when they're 90 degrees apart, like the modulation goes the other way. Like these guys are seeing gravitational waves. They're like the ones for LIGO, except the period is like a year, right? Like one period of this wave is like a whole observing run for LIGO. And these are from like solar, like black holes that weigh like 1 billion times the mass of the sun. These are big churning things in the center of galaxies. There are a bunch of people with pulsar timing arrays, Parkes in Australia, the European one, the Indian one, the Chinese one, Meerkat in South Africa. These guys are all collaborating in the International Pulsar Timing Array. They say they're going to have another data release in a year or two. I think that's going to be super, super exciting. We will see. And with that, I'm going to stop. I think it's a very exciting time to be doing this new kind of astronomy. We are very fortunate to be able to see lots of signals. We're very fortunate to have lots of good ideas about how to see more signals. And there's a lot of interesting ideas. Like I think this field is just getting started. If you come back and, well, these guys come back in 10 years, like there's going to be a whole bunch of new stuff that really surprises people. And so I feel very thankful that I'm kind of working on it right now. I'm also very thankful that you guys have come out to hear me talk about it on such a terrible night. And very thankful for all of you and your public support of science and the cool stuff that we're doing. And I'm really glad to be able to share it with you. So with that, I'm going to stop and let people ask questions.
Nice talk. And sorry, we didn't understand one thing about this instability. So if black hole is like large, like 85 times solar mass, then there is an instability, or then how do we have this 1,000? Yeah,
so I think there are two questions there. The first is about the instability, and the second is about how do you get 1,000 solar mass black hole. So the first one, so the 85 solar mass black hole itself isn't stable. It's the thing before that. So to form a black hole, you start with a bunch of matter, and then it eventually gets to be so much that it collapses on itself under the force of gravity. And the result is a black hole, but the thing that you start with is just like the center of a burning sun. The theory, which, you gotta wonder, right? The theory is that when the thing that you start with gets to be more than about 65 solar masses, it can't collapse, because the first thing it does is it explodes, right? So if you have 30 solar masses of, oxygen in the middle of a burning star, it can cool off and collapse into a black hole. If you have 65, it can't, right? Because the whole thing becomes unstable. And so, let me back up a couple of slides, because there's something else to say here. And so it's not clear, so using that mechanism, you can't make an 85 solar mass black hole, because there's just not enough stuff, right? But we know there's a 4 million solar mass black hole in the center of our galaxy, so you might ask, how did it get there? Nobody knows. Nobody actually knows, right? This is particularly interesting because the result of this is 142 solar mass black hole. It's called an intermediate mass black hole. It is the first one that anyone has ever measured, right? And so you might think, oh, I could take 2 medium-sized black holes and make a big black hole, and then take 2 big black holes and make a really big black hole. Take 2 really big black holes, and can work your way up to the center of the galaxy. It's not impossible, right? We'll see.
Thank you very much.
Yeah.
So you say that the strain for the LIGO can measure is like 10 to the minus 18th meters. And obviously the signal attenuates as with distance. So I'm curious, what would that equate to at the black holes? You know, that extremely distorted space-time between the two just before they merge that you showed. You know, what would that be, meters or kilometers of space just ripping apart? Or?
Probably meters. It's been a long time since I've done that number. The amplitude falls off as 1 over r, which is different than the light from a star, which the brightness falls as r squared. So you can take what was that thing? How far was it? Oh, I should remember this. Can't remember.
1.3 billion light years.
1.3 billion light years, and like go back and say, well, you know, I'm going to go out a couple of kilometers, right, so I don't get whacked by the black hole going past, and just like scale it back by the ratio of the distance. I'm not going to try to do that when I'm standing here. I'll get it wrong. Yeah, it's a lot though. Yeah.
You indicated that the different forms of radiation at higher frequencies or higher energy arrived at the Earth at different times.
Yeah.
Don't they all travel at the speed of light? Could you explain that?
Well, mostly they arrive. Well, so here's the timeline, right? So I'll just throw in a little pitch for the cool kind of physics you can do. The gravitational waves and the first signals, the gamma rays, got here within 1.7 seconds. This is the first time, this is the best measurement of the speed of gravity that anyone has done, because after traveling for 130 million years, the two signals got here within 1.7 seconds of each other. So we can't prove that the speed of gravity is c, but it's pretty close. So the rest of it is, you know, what you're looking at is this giant fireball. As those neutron stars come in, the outer edges actually come off of the neutron star. And so by the time the centers actually smack into each other, it's in the middle of this cloud of nuclear stuff. And so the signals propagate out of that. That becomes like that, you know, there's jets that come out the axis. That whole thing gets really hot. The light, like the center of our star, like our sun, right, takes a long time for those photons to wiggle their way out of our sun. So what you're seeing there is both the time for the signals to propagate out from the center of that big fireball, and then the fireball to cool off. Why did the radio signals not start until 9 days afterwards? I don't think anyone really knows that. I don't think it's because of the travel time. I think it's because of the processes that form those radio waves. Yeah. We want to see some more signals so I can get a better answer.
So given the success of LIGO, and maybe coupled with that of like Gravity Probe B, I mean, are we at a point now where we can say there is such a thing as a graviton or a unit of space-time? And if so, does it make sense to maybe look for an equation set where we can relate the graviton to the gravity flux in a way that Maxwell's equations relate an electron to electromagnetism?
So I am not enough of a theorist to give you a good answer to that, but I'll tell you a couple of things. It's nice to see a Gravity Probe B guy here. Like the way that our mirrors are attached to each other is the same bonding process that was developed for GPB. My lab was actually in the same space where the spheres were polished, so thanks. The one thing that we're doing, so the one thing that we're trying to do with gravitons, it's likely that the mass of the graviton is 0. If it's not 0, then it travels slightly slower than the speed of light, and there's maybe some dispersion on it. There's recently a paper looking at the general relativity impacts of what we're seeing, trying to look at all of the various things that we see. They've actually set a new limit, an upper limit on the mass of the graviton, which I actually heard this yesterday in a lab meeting because they changed it because they did the statistics wrong, and it went from like 1.2 up to 3 10 to the minus 23 EV is the mass of the graviton, right? The person, Beverly, was like, it's still 0, but yeah. So I actually told her, I'm like, I'm so glad you said that because like it might come up tomorrow. And thanks. So I don't think so. We'll see. But people are asking really significant questions about general relativity because this is one of the best ways where you can test them, right? Because the fields get really strong, the signals are very interesting, and you can't do tests like this of general relativity here on the Earth. You need to do it somewhere else. We know that there's some problems with the theory of general relativity, right? We know it, like, it just doesn't make sense to have a singularity at the center of a black hole. But what is the right theory? Like, we don't know. So it's, yeah, we'll see. Thank you.
Can you go back to that butterfly diagram of the mergers of the various objects? Does that have an x-axis, or is the x-axis is that just an artistic?
It's just artistic.
It's just artistic.
It's
Okay.
just arranged to make it look cool. There's another one of these where it's arranged by time, and then you can actually figure out which event is which. No, it's just to make it look cool.
And what's with the yellow? What are the yellow objects merging with? What are the red objects?
So the red objects are low mass X-ray binaries. They're not, so what those are, you can see those electromagnetically, and that's where you have some kind of a black hole next to some kind of a normal star, and the black hole is eating its companion. And so you can measure things about that and infer that there must be a black hole in the center of it.
So a merger hasn't happened yet.
Now, well, it's kind of eating its companion, so it's kind of happens slowly. Yeah? Yeah, right? It's a very different kind of event. These are neutron stars. I think these are all pulsars. I'm not confident of that, but I think so. Most of them are certainly neutron stars, yeah. Are certainly pulsars, yeah.
First of all, thank you very much for a fantastic presentation. Really enjoyed it. I'm going to come from a little practical standpoint. I know you're someone who enjoys the tinkering and the actual construction of these amazing machines. Have you encountered new technologies and stuff through this that will end up with, shall we say, less stellar-oriented application?
Yes, clearly we definitely have. The laser that LIGO uses, one of the main drivers for that laser development was LIGO applications. That's the NPRO, which if people around here are familiar with lasers, actually Bob Beyer, my boss, invented that. And those are now ubiquitous, both in industry and in science. The coating technologies that we're developing for the mirrors are seeing a lot of application in precision metrology, timekeeping things. The other thing that there's a bunch of technologies like that. The other thing that we do is we have graduate students who come and work on LIGO to do some cool project, and then they get trained in doing precision instrumentation or precision data analysis, and then they go off. I had a grad student who went and founded a wind power company across the bay. So I think both the technology and the people that we're training are great outputs from this kind of science.
Thank you.
I have an instrumentation question. I sort of remembered at first when the observatory, the LIGO came online, it didn't detect anything for a while.
That's true.
And then you changed something, made an upgrade, and then all of a sudden you got something. Can you tell us what upgrade you made, or what was the breakthrough that allowed you to finally get signal?
Yeah, so we ran initial LIGO for a number of years and never saw anything. We upgraded to Advanced LIGO, and Advanced LIGO had a couple of important changes. The seismic isolation and the suspensions got much better. The laser power went up. Instead of hanging a mirror like this big from a steel wire, Now we have a 4-stage suspension hanging on glass fibers. For example, yeah, so there's more power, so you can do a better job of doing the photon statistics. The seismic and suspension, the isolation system is much better. Actually, the noise performance of Advanced LIGO isn't that much better than initial LIGO. It's just that if you can cut your noise in two, you can see twice as far out into space, and now you can see 8 times the volume. And so your event rate starts to go up really rapidly once you get far enough out that you can see something. So I think those two major changes and a lot of little things are really what kind of set us over the edge.
Thanks.
Yeah.
So I have an observation and an unrelated question. It looks to me like it's easy to make 85 solar mass black holes because you found a bunch of them already.
Well, no, see, that's a really good point, right? So these merger results, like there's a bunch of stuff at 85 solar masses. And that's certainly one of the ways that you can do it. But here's the thing. I'm going to let you finish, ask your question in just a second. So these are results of a merger. They are spinning really, really fast. So if you can get more of the ring of the in spiral of the merger signal, you can actually measure the spins, but you need more than a couple of cycles, right? So one of the things that we hope to see with better instruments is to push down the frequency range to which we can see stuff, so we can watch those things spin in, and then we can tell you, yeah, like there's a black hole, it's spinning like crazy, right? And it's somehow paired up with another one, which is also spinning like crazy in another direction. So somehow these two guys got together later in life, right? Right?
Okay, so
Well spotted, thank you.
you're a mirror guy. I'll ask a mirror question. You're measuring the 1,000th of a proton using something made of atoms.
Yeah.
How in the heck do you know where the edge of a mirror is?
Averaging.
It's all averaging.
It's averaging, yeah, yeah. Well, so the proton, so there are two things. I mean, one is that you're averaging, right? The spots, the LIGO beam spots are kind of this big, 6 centimeter radius, 6 centimeter diameter, about this big. And so you're averaging over a lot of surface. The other thing is that, and you're also averaging over some depth, right? Because the light goes in a couple of layers for the kind of mirrors that we're using. So it ends up going a couple of microns in. So you're actually measuring a bunch of stuff. The other thing is that we're not measuring the arm length exactly, right? What we're measuring is fluctuations in the arm length. And this is really important for measurements like that, because, there are a bunch of atoms in there, but they're not going anywhere, right? They're kind of wiggling around because they're warm, but basically they're all fixed in place. So you can do, because you're just looking for these little vibrations in the arms, it allows you to make much more precise measurements.
All right, we'll have 3 more questions.
Okay.
Thank you for the talk. I'm wondering, how do you measure or calculate the mass of the black holes from the gravitational waves?
This is a good question. I like this question. Because what you do, so unlike most kinds of measurements of stuff in outer space, the gravitational wave signal gives you a lot of information about the source. So you got these two objects, they're going around each other. Because they're accelerating, they are emitting gravitational radiation. And as they emit gravitational radiation, the orbit shrinks and it changes. So the rate, you can see this starts at a low frequency and then it gets faster and faster and faster. The rate at which it changes tells you the mass of the objects. What's even cooler is that once you know the mass of the objects, you can then say, well, I know how big the gravitational wave was when it was emitted. I know how big it is when it gets to me. So you can actually use it to find the distance to the objects. There's an uncertainty because you don't quite know if it's like going around like this, or like if it's face on to your edge on, like it's like a record, and you don't know which quite way it's pointed. But the shape of this waveform gives you a lot of information. And then what we do is you just model a bunch of parameter sets with your supercomputers, right? And you see which parameter set fits the data the best, and that's the one that you pick for the parameter estimation. There's a whole team of folks in LIGO and Virgo who do parameter estimation. Yeah.
A very related question, I think, is what is the information contained in the frequency of the waves between like a 1-year frequency and the ones that LIGO found? What information is in there?
Right, so this is just like the last 200 milliseconds of lifespan of this binary system. When you look down at lower frequencies, it's either because the black holes are much farther apart and they're just kind of cruising around, or they're much bigger. And so you can look at them for different masses. The different masses, typically the bigger masses that you'll see, the lower frequency stuff that you can see with a gravitational wave detector probably has bigger masses, because that gives you a big enough signal to measure. So that tells you about stuff that's on its way to forming the big black hole in the middle of our galaxy, or it tells you like that, for these billion solar masses that the Pulsar timing array, like that's probably 2 galaxies that went past each other, and the black holes in the middle kind of captured each other and started merging or something like that. So that's one thing, right? Because different kinds of black holes are doing different things in the universe. The other thing is that, let's say you have 2 30 solar mass black holes and they're going around each other. They'll start off at low frequencies because they're a long way apart and they're just kind of doing their thing, and eventually they'll spiral in, and we can see the last 200 milliseconds with LIGO. But some of that stuff is going to go through the band for LISA, right? So there's a lot of events where you think maybe you can see it first in LISA, and then some months or a year later, like as that thing gets smaller and smaller and faster, you'll see it again in LIGO, which would be really cool because you're like, in 8 months, over there, like there's going to be a heck of an explosion. Like make sure you're looking, right? So people are excited about that too.
It seems like your optics are fairly large, and I'm curious on how you move them in order to make sure that the phase between the 2 arms is opposite.
Yeah, so we do have to very precisely control the mirrors, because for that 300 bounces in the arms, the arms have to be what's called resonant. And we have actuators. So there's 7 stages of isolation, from the mirrors themselves all the way up the chain through the seismic isolation to the external. Every stage has an actuator on it. We have electrostatic actuators on back of the mirrors. So these are just little electrostatic plates that push against what's called the polarizability of the glass. So you can directly push on the mirrors even without touching them. As you move up the chain, there are little magnets and coils. And then as you get in the seismic isolation system, there are big magnets and coils. And on the outside, we have laminar flow hydraulics, because as the tides go past, the arms stretch out by like 120 microns with the tides. So you have to be able to track that stuff. So there's actuators through the whole thing. It's an interesting design problem.
That's awesome. Thanks. All right, let's thank Dr. Lantz again.